All right, we'll give it a go then. So, morning everybody. My name is Paul McLoughlin, and I'm going to talk to you today with my colleague Sachin Kamboj about the next generation microservices project at Bloomberg, which is kind of powered by Kubernetes, obviously. So we're going to spend the next 30 or 40 minutes talking about a few different things. We're going to talk about our company, explain who we are so you have a bit of context and you can understand some of the decisions we've made. We're going to talk to you about this microservice platform that we built and we give out to various departments within our organization. It's a slight twist on a typical kind of microservice idea. We're also going to talk about our use of Kubernetes and specifically how we went about evaluating whether the hype and the reality were matched, some of the problems we ran into, and some of the pain points that we had. So if nothing else, maybe that kind of latter half of the presentation will give you some gotchas and some answers to those, which maybe will save you some time. So Bloomberg, who are we? So if any of you work within the financial services industry, you're going to be very familiar with who we are. We're kind of omnipresent within banks, hedge funds, investment shops, anything like that. If not, then maybe you are more familiar with the fact that we have a TV channel. So if you turn on TV in a hotel room, we're always there. If not even that, then maybe you've heard of Mike Bloomberg, who is the mayor of New York. So Mike Bloomberg was one of the core founders, the four founders of the company. It wasn't always called Bloomberg. But he founded the company with those three other people 35 years ago. We're privately held, and one of the nice things that I think about working for this company as a software developer is that all of those founders were also software developers or systems development people. So first and foremost, we very much are a software company. We have 90,000 employees. We have offices everywhere, it seems. We have around about 5,000 engineers, primarily based in New York, London, but we have offices in various other places. We have the TV channel. We have radio channels. We have Bloomberg.com, which is a great website. These guys over there run it. It's very helpful if you're trying to manage your personal finances. We also have a magazine, which we publish on a weekly basis, an old-fashioned hard copy thing. And that has a circulation of almost 1 million. It's sent out to 150 different countries. All of those other bits, though, are more the sideline. They're not the core part of our business. So if ever any of you have heard of Bloomberg, you might have heard of something called the Bloomberg Terminal. And the terminal is basically our subscription service. So what people do is they pay us to get access to our terminal, and that gives them any kind of data they want, which should be kind of anything they can imagine relating to a whole series of different industries. So like a lot of you, I guess, we deal with data. If you think about financial data, the kind of obvious thing that springs to mind would be something like the price of a ticker or a stock on an exchange. So something like an IBM, a Microsoft, or Google, what is it currently trading at? We do that, but that's only a very, very small part of what we do. That's something that's very easy to parse, very structured, and is very clean specification. Our mandate and what we do is we aim to source absolutely anything and everything we can find in the wider world which pertains to the financial markets, the insurance industry, legal systems, and the US government. So when we come back and think again about the price of IBM today, it's all the many, many factors which drive that price. It's the second and third level thinking that people have, and we have to try and second guess all the kind of information they're going to want at their fingertips to be able to make a determination on that stock. Furthermore, an important thing to point out, it's not just the current value of these pieces of information. We want point-in-time data of all this information. So what I mean by point-in-time is we have the current representation or the current value of a piece of data, but we want to be able to see historically how that data has evolved, both in terms of its absolute value, but also its structure. So maybe the value of a piece of data is altered structurally, and it's obviously altered in absolute terms. Think about a weather forecast. We have the weather forecast for Saturday. As we get closer to Saturday, we're still interested in what the weather forecast is for Saturday, but we can see the evolution of that forecast. An important thing to point out as well is that the kind of data we deal with has to be very, very high precision. People make decisions which have a monetary value of hundreds of millions or billions of dollars. So we cannot afford to be incorrect or wrong with our data. So it's very, very important the data that comes through our company is correct and accurate. So before we get into specifics of exactly what our project is, just to give you a more concrete example. So if you kind of imagine, let's say we run a company, and our company is something to do with renewable energy. Maybe we sell wind turbines or solar panels, something like that. We're going to be very interested in weather. We're going to be very interested if there is a hurricane or some kind of natural disaster expected. We're going to be very interested in weather forecasts and whether, for example, there is enough wind in this particular area for us to consider selling wind turbines there. I'm going to have to manufacture these things, so I'm going to need a lot of information about the commodity market, what kind of price I should lock in, whether I should wait a little bit, whether I should just proceed as is. I'm going to want to know about government legislation that potentially could be coming up and affecting me. I'm going to want to know about grants and rebates and whatever else the government is doing. I'm going to want to know about the state of the economy. Maybe people don't actually have money to be able to spend. Maybe this particular geographic area, people are not particularly keen on renewable energy. And there's kind of a million other different areas or factors which could influence and be very, very useful to me as our business owner. So we have around about 3,000 employees in our data division, and their job is basically to second guess what our customers might want. And if there is anything missing, then the customers can ask the sales rep for it, and we will go and acquire it for them. So their job is basically to source as much information as possible. So, you know, we deal with a lot of data from a lot of different sources, which updates extremely frequently. This is the development team. So you have Michael and Mika over there and Sachin down here. Please come and talk to us. This presentation is more about Kubernetes. But this is a production system which has been running for a number of months at scale. So we have a lot of experience with Prometheus and alternatives, Fluentd and alternatives, configuration management tools. So please come and pick our brains. We're happy to help. So this was kind of like our mission statement. So we wanted to build some kind of infrastructure that would allow non-engineers, so this data division, these people who had excellent domain knowledge, as well as engineers like ourselves, to be able to deploy code effortlessly. And if possible, we wanted to be able to deploy our code with a higher level of confidence than we currently do. So what we did is we came up with this DTP thing, Data Technologies Pipeline. And this is the platform that we've built, which has been in production in Bloomberg for approximately a year. It's going to provide a great benefit to that data division as well as our own department. The aim is, obviously, this is why we're all at this conference, but Kubernetes takes care of an awful lot of the cross-cutting concerns that we would have and the non-functional requirements that are very, very common. So it's very, very important that, or it's very nice that I, as a developer, can focus more on the problem at hand rather than having to build a system, own servers, and all the other kind of operational concerns that go around that, which take up an awful lot of time. So the aim with this platform was to kind of minimize that cost, make it so that we had single-click deployment, and we could push code out in production exceptionally easily. So microservices. So these days tend to be the answer to all problems. We won't have a debate about what that means, but to us it was basically about the idea that they're small, they're focused, they do one thing and do one thing well. In terms of what we expected from people who deploy services on our platform, we wanted them to guarantee that they had a minimal API and very clearly defined dependencies, and ideally minimal dependencies as well. We also wanted them to make sure they had good code coverage, so good unit tests, good acceptance tests, and those tests should pass. And in exchange for that, we would build this platform that would empower them. We also, sorry, just to add there, we also wanted to make sure that we didn't have any unnecessary restrictions. So we didn't want it to be restricted to a single language. People should be able to, it should be language agnostic. We shouldn't be overly concerned with only throughput below a certain number or only latency above a certain number. So the thing that we built was this next generation microservices. So the first point up there is where we start to differ from the kind of normal example of things, the normal way of the world. So we very clearly and very explicitly wanted people to test in production. And that was a huge thing for us. We wanted to handle all the plumbing. We wanted this single-click deployment or potentially some kind of push-on-green deployment scenario. And we wanted all the good things that Kubernetes would bring to the table. We also wanted the ability to self-host a lot of the services which define our platform within our platform, and that's something that we've also done in the same way that Kubernetes is moving along those lines. Testing in production is still up there, and the obvious thing is if you have a conversation with some people, they would look at you very strangely and say that must be a bad thing. This is a famous quote from Fred Brooks in the Mythical Man Month. So all programmers are optimists, obviously. Just to paraphrase, maybe it's the curious nature that our profession requires and the kind of uncertainty involved that kind of drives this and requires this of us. But these two highlighted sentences at the back are things that I've said many times and I've heard many, many times this week, I'm sure. So this time it will surely run, and I've just found the last bug. There are no more, don't worry. It'll be fine this time. This is the typical release cycle that I'm guessing a lot of people have. We have some kind of a production environment, and then we have a series of pre-production stages. We write our code, we write a series of tests, we run the tests, and hopefully they'll all pass. If not, we'll fix them. At some point in our process, we're going to be happy that all the tests are passing, and we're going to iterate through, and we're going to deploy that into the next environment up. So we deploy it in there. It's going to go through some other kind of testing phase, at which point, again, we'll ascertain, is this working or not? Now, if it's not, then we loop back, we run some fixing code model, and we push it back out again into the staging environment. But if everything is still working, all our tests are passed, then at that point, we should be happy to proceed to production, right? So we deploy it into production. Maybe we run a little bit of testing. Our customer starts using our service, or our client does. And then we have the fabulous thing where we find out that something somehow is different and has changed. So we're not quite sure what the hell's going on because we've done loads of testing, we've been exceptionally well behaved, but still it doesn't work. So why? Why is this the case? So differences, obviously. So differences in the environment. There are the kind of disturbing differences which we should never have, but unfortunately do arise. So differences potentially in hardware, in the OS, permissions, maybe with the user profile, any number of things. Maybe we've iterated through too many times and something's going wrong. Maybe there are other things running on that box which is affecting our dependencies and causing us to break in a production environment. And in our particular case, we have a lot of data. This data is highly complex and highly interdependent, and that often causes problems. It's frequently the case that we have excellent data in production, but as you go down through the environments, the data degrades quite rapidly. And also, we have to rely on an awful lot of third-party systems, other groups, and maybe they just aren't as well behaved as we are. Maybe they don't even have a dev version of their system. So what we have is we end up in this typical kind of release cycle, which certainly was familiar to us, and I guess is pretty common out there. So we code, we deploy, maybe it works, maybe it breaks, we roll it back, and then we repeat and repeat. The idea is, or the fundamental thing is here, unless we can guarantee that our non-production environment is exactly identical to production, there's no way we can be 100% confident that when we push out to production, things will definitely work. And try as hard as we can, it seems to be impossible for us at least to ensure that we have some kind of a pre-production stage where production is exactly identical. So this is where we come back to our idea of production and testing to ensure that when we go to production, we can be confident that things are going to work. So there's a little tweak to what people normally do. We're going to describe it now in a second. So obviously, we're going to write our code. We're going to deploy it, and we're deploying a version which is a canary version. So you can see it's red, and that means that it's not actually handling or delivering production responses out to clients. It's still going to receive the production requests, but it's not going to handle the responses back out. We're going to send in a bunch of sample inputs. We're going to check the output, see if we're happy or not. If we aren't, then we're obviously going to make some changes, redeploy, and that version 1 is going to kind of iterate. At some point, we're going to test this. We're going to test the inputs. We're going to test the outputs. And we're going to be confident that the version that we just pushed out is correct and proper and should go out and be handling responses back out to our customers or clients. And that's now the publishing version in production. So we have this one version running in production. Something happens. We need to make a change. So we write some more code. We deploy it. And we deploy a canary release into production. Now, obviously, one of the requirements that we have and one of the kind of deals we make with the people who use our platform is that if you're going to have multiple versions of a service running in production, then you have to definitely not do certain things. So if this code, for example, was placed in trades, this would be very, very bad if we had two services placed in the same trades. So it's important that we have a restriction, and the idea is that people should not touch systems which have side effects. So for example, we must not write to a database, we must not write to a file system, we must not send emails. There are a great many things. This may seem exceptionally restrictive, but we don't think it is, and we'll come back to that in a minute or so. So we pushed out a canary release which has some modified business logic in it. And then we look at that, and again, all the requests are coming into the system, and there is a mirroring system which is mirroring all the requests in reasonable time to all the different versions of this particular service. We check, we leave it running. Are we happy? No, we decide we're not happy. So we make some more changes, and we deploy another alternate version of this service. So now we have the publishing version of our service, which is handling our production requests, in which our users, our clients, consumers, whoever are using. And then we have 2 canary releases, which are running with modified business logic. Maybe, and for some reason, we're not happy that they should go out. Again, we check the input, we're checking the output for each of the different versions. If we're happy, then we can promote that one to be the publishing version, and then the other 2 revert to being canary releases. So now release 3 is the version of this particular service, which is handling production requests. So, where are we? We're in a position now where I don't really need a dev environment if I'm writing this code. So hopefully, we can deploy our code within this system. The platform is going to take care of all the operational concerns, all the non-functional requirements. I can focus on the particular problem at hand, and I can have multiple versions. We do actually still have dev and all the other environments, but they're less and less used. The important thing here is our idea that microservices must be pure, and there must be no alterations to external state. So what I mentioned before was the obvious example about a trading system. There are obvious examples about updating databases, sending emails, touching the file system, any number of things. When we thought about this, we thought about how we structured our code. And the common paradigm within software development is you separate what varies from what stays the same. And in terms of and taking that analogy a little bit further, we wanted to think about the frequency of updates, the frequency of what varies. And to us, if we think about a service that gives us the capability to place a trade, interact with the file system, a mail system, anything like that, our interaction with those services does not change or does not vary typically. What varies is the object or the data payload that we give to those services or those other systems. So what we've done here is we've enforced this requirement on our users to make sure that they separate the business logic from the logic which touches these stateful systems which have side effects. Because they're not doing this, so for example, if we have some logic which determines whether or not we should place a trade, we have the logic running in a microservice, and we have many different versions of it, and the output of this service is just a tuple telling us what kind of trade we should place. And then we have created another system which handles interactions with those services which have side effects. So by doing this, we have the ability to run many multiple versions of the service in production. And for these people in this data division, these 3,000 people, to do the thing they know best, which is write simple code, which focuses on the area where they're the experts rather than us. There are also nice things. I mentioned before about the ability we have for point-in-time data stores. So we have a whole suite of version systems, version databases, and this is something that's very, very helpful. So we can go back, and if we push in a new version of a microservice, we have all the requests and responses cached from all previous interactions that the publishing version made. And we can go back and have a point-in-time request on these other systems to say, I want the record for this particular key, but I want it as of this particular date rather than the current date. And that means that we can push a new version of our microservice out into production as a canary release and backtest it very effectively with actual live requests and responses from external systems. The last bit here really is, it's pretty standard. Everybody's doing it. So how do people write their code? So we push our code to GitHub, or whoever wants to write a microservice pushes their code to GitHub. You tag it. We give people the ability to set envars, have secrets, and then it's entirely on a user's hands to say, of those canary releases, maybe we nuke one and it's no longer active. Maybe we switch, which is the publishing version. All of that is entirely in their hands. So on to the next part, which Sachin will take you through.
Okay, thank you, Paul. Hello, everyone. My name is Sachin Kamboj, and I'm basically going to discuss the nuts and bolts of our system, how we built the system using Kubernetes, and some of the lessons we learned along the way, some of the pitfalls we encountered, and our general approach, and hopefully you can learn from that approach and perhaps not make the same mistakes that we made. Okay, so when we set out like building the system that could be used by non-engineers and engineers like Paul mentioned, we had a shopping list of things that we really wanted. And what was in that shopping list? Well, we wanted isolation. This is the basic concept that if we have a microservice that might have a bug in it or a flaw or might be malicious, we don't want it to affect any other microservice, and we specifically don't want it to take down the whole system. We want rendering of dependencies. So this is the concept where we have a microservice. It depends on versions XYZ of libraries A, B, and C, and we have another microservice that depends on versions TUV of the exact same set of libraries, A, B, and C, and we want those two microservices to be able to coexist with each other and to be able to run simultaneously and not affect each other. We wanted orchestration, the basic idea being that we have microservices, we want to deploy them across different nodes, we want to make sure that they're deployed in different availability zones, and the idea that we want to be able to auto-scale them depending on the amount of traffic that we get, depending on the CPU usage, depending on various other constraints. And like Paul mentioned, we wanted ease of deployment, typically a single-click deployment, the ability to run multiple versions of a microservice in parallel, and the basic idea of having rolling updates and starting a new version up and then taking down another version. And finally, we wanted self-healing. So this is the idea: if we have a microservice that's crashing, we should be able to bring it back up and go on from there and hopefully try to figure out why that microservice is crashing. So in addition to all these things, the last 2 points are pretty obvious. We want the whole system to be very stable and reliable and to have high availability. Okay, so that's our shopping list. We're at Kubernetes conference, and Kubernetes is obviously the best thing since sliced bread. So we just deploy our system on Kubernetes. It all works. We all go home. Everybody is happy. Everything works great. Awesome. Unfortunately, the real world is never as simple and not exactly the same as an ideal world. So whenever you have a piece of technology that's being touted as the next best thing since sliced bread, it's being touted as, this is the thing to use, it's always helpful to take it with a grain of salt, to show a healthy degree of skepticism towards it, and to actually really test it out, take it through the paces, and try to figure out it's making these awesome claims, does it live up to them? So what I want to cover in this next couple of slides is how we really tested out the system, how we got comfortable with it, and what we learned along the way. And hopefully you can learn from our experience. It's obviously, there's no way this is going to be an exhaustive list of the things that we learned because we don't have the time to go through them, but you should come and talk to all of us. Okay. Sorry about that. I don't know how we exited. Okay, so back to our shopping list. I would argue that Docker does a very good job of packaging some great Linux features like C groups, namespaces, capabilities that gives us excellent isolation and rendering of dependencies. And Kubernetes was really designed for the concept of having orchestration, easy deployment, auto-scaling, the things like that. But what we really wanted to determine was, if we deployed a cluster using Kubernetes, is it stable? Is it reliable? Is it highly available? And before I continue, I just wanted to mention 2 caveats. The first one is that Kubernetes is a very fast-moving target, so anything that I'm mentioning right now and that's true right now is probably not going to be true a month down the line, and it's definitely not going to be true a year down the line. And the second thing is, none of the points that I'm going to mention should be taken as a criticism of Kubernetes itself. It's more about how we went about testing the system, deploying it, and learning from our experiences. And hopefully you can take those methods, or you can take something from our experience and use it in your own enterprises and your own clusters. So with that in mind, I just wanted to briefly discuss our basic architecture so that we're all on the same page and we all understand, how we work. So we have any number of data centers. For space restrictions, I can only show 2 on the slide, but we have multiple data centers, and we have multiple Kubernetes clusters running on those data centers. They're more or less, or actually they're supposed to be exactly identical. So our Kubernetes clusters are supposed to be identical across data centers. We have 5 master nodes. What this means is that we are able to survive 2 node failures, and then we have any number of worker nodes, and all our data centers are combined together using a load balancer. Diving in a little bit deeper into what our master nodes look like, at the bottom you can see we have flannel D. That's basically to allow communication between pods running on 2 different nodes. Like I mentioned, we're using Docker for isolation, windowing. And then we have kubelet and kubeproxy, which is running on every single node. We also have this thing called a K8s API server proxy, and I'm going to go into the details of why we need that and what that is in a little bit. So keep that in mind, that there's something that I haven't explained right now. And finally, this is a master node, so we obviously need the master components, which means we have the API server, we have the scheduler, we have the controller manager, we have etcd as our source of truth, and we have kubedns. Going on to a worker node, it looks very, very similar to a master node. So obviously we have flannelD Docker, we have the various components like kubelet and kubeproxy. Again, we have the API server proxy. But instead of the master components, which is the API server scheduler and controller manager, we have pods. And even though over here it shows microservice pod 1, microservice pod 2, in some cases, or in a lot of cases, there might be the exact same version of the microservice. Or as Paul mentioned, there might be different versions of the same microservice running. And finally, we have a reverse proxy to tie it all together and so that we can access the various pods. Okay. So now that we have a basic understanding of our architecture and a common set of things to talk about, let's discuss about how we evaluated our system. We are firm believers in the maxim that the only real way to know how a system works is to try to break it. So we wrote this piece of tool that's called Powerful Seal. It's our chaos monkey. And the idea behind Powerful Seal is it breaks things so that we can understand how things work. So what can we do with Powerful Seal? I'm not sure if you can read the slides, but just to go through them, it allows us to view an inventory of all the nodes in our system. So we can see, well, what are the nodes in the system? We can group them by availability zones. We can group them by components, so we can see which ones are master nodes, which ones are worker nodes. And have a good idea of what's in our system. The other thing that it allows us to do is look at the status of various components that are running on those particular nodes. So if we wanted to look at the status of, let's say, the kubelet node that was running on all the nodes on a particular availability zone, we can do that. We can look at the status of, let's say, the API server or the master and collect the status from all the various components. And it also allows us to give us the ability to tail or collect logs across nodes. So what this means is if we wanted to collect the logs from all the API servers, from all the masters, we can do that. If we wanted to collect logs from, let's say, all the kubelet components from all the nodes in a particular availability zone, we can do that. And finally, it really wouldn't be much of a chaos monkey if it wasn't able to take things down. And part of the reason why we designed the system was mainly to take things down. So what we can do is we can take down a node, we can take down an entire availability zone, and we can also do things like watch the things go down in real time, see what's happening, and once things have gone down, we can try and see collect logs from them and see what really happened. So this is some great work that Miko did in building this system. Okay, so now we have Powerful Seal. We have the ability to take down nodes. We have the ability to take down components. We also have the ability to take down things in production, run in auto smash mode when it's continuously running. And what can be learned? So this is the slide of lessons learned, or how we learned to stop worrying and love Kubernetes. I'm not going to go through all the lessons learned, all the pain points, all the things that we experienced. Come talk to us if you want to know more. I'm only going to discuss 3 stories. And these 3 stories are kind of illustrative of the things that we tried, the things that we learned, and some lessons that you can do. Okay, so the first story. This was very early on. We started out with deploying a Kubernetes cluster, deploying a couple of pods, running microservices in them, testing it out, and we're like, okay, great, this works. Let's take things down. So we used powerful seal. We took down one particular node. We decided to take down not only any node, we decided to take down a master node. And because we were lazy and we just decided we picked the first master. So we took down the first master node, and things didn't quite work as expected. Things broke. So why was this? Well, it turns out that kubelet and some various other Kubernetes components can't really deal with multiple API servers, which means that even though kubelet accepts a command line flag that allows you to specify multiple API servers, in actual fact, what kubelet does is it talks to the first API server, tries to contact it. If it can't reach the first API server, it does not even try to go to the next one. And this was very, very surprising to us. So there are outstanding issues on GitHub, and you can read up on that. The reason, if this is a really big deal, but we're surprised that, other people did not face that. And the reason for that is that the way people deployed them, they run the API server behind some kind of a load balancer that's provided by the Google Cloud Engine or by AWS, which does the proxying to multiple API servers. We were running on bare metal or OpenStack where we didn't have access to that, or we didn't know we needed access to that. So we ran into this issue very early on. The way we solved this problem was, remember when I discussed the architecture slides, when I was discussing the various nodes and I had a K8s API server proxy? So we're running a proxy server on every single node, and its only job is to proxy requests going to the API server amongst the various master nodes, so that even if the first API server goes down, it's able to contact the various other API servers. So this is an example of something that we wouldn't have learned if we didn't take things down and figure it out. Okay, our second example. So we had our Kubernetes cluster running for a while. Things were working great. And very soon, once we found out that for some reason there were pods running on a particular node that weren't able to communicate with pods running on another node. So why is that? Okay, so on further investigation, we found out flannelD, which handles the communication between pods that is running on one node with pods that are running on the other node, crashed on a particular node and was no longer running. And specifically, it had died because of a sick pipe. So first question, well, why did it die? We found out what really happens is we had a microservice that was generating a shit ton of logs. And the microservice, and we were using Docker, which was actually using the journald log driver. And at some point in time, journald could not handle that number of logs, so journald crashed. Journald was restarted by systemd. However, what happens when you have a process that's trying to write to an open file descriptor and whatever's listening at the other end of the file descriptor crashes? You get a sick pipe. Unless you handle sick pipe well in that situation, you are going to crash. Also, how many of you have actually written code in which you try to handle errors in writing to std out or std error? I bet you almost no one. We don't expect std out or std error to crash, yet we expect our microservices, the standard idea is, oh, just write your logs to std out and std error, and we'll collect them for you, and we'll display them for you in a nice way. Okay, so flannelD was crashing. Now here's the other interesting part of the situation. It crashed with a sick pipe, and systemd, which is responsible for starting these services and restarting them, considers sick pipe to be one of the normal conditions for exit, which means that if a process goes down because of sick pipe, it will not be restarted. Okay, so how do we fix this issue? Well, number one, we make sure Flannel restarts no matter what happens. The other way we did it was we developed a tool which we called Goldpinger. What this real tool does is it basically runs as a daemon set, so it's running a pod on every single node. And its only job is to communicate with pods on other nodes and try to ping them using an HTTP ping. And if it can reach the other nodes, okay, things are good, great. If not, it will tell us about it. So this is the way in which we can graph the problem. We can see what nodes are read. We can dive down and see which nodes can't communicate to what other nodes. And we have hooked this up with Prometheus and alerting so that we're able to tie it all together, and the moment communication between any two nodes fails, we're informed about it so that we can look at it and try to figure out what's happening. So that's our next tool. The lesson learned over here is basically whenever you have a complex system with with a number of moving parts and a number of interdependent components, you can have a failure in one component, which is like a microservice that's writing too many logs or something like that, cause a completely separate system that's not a dependency and that has nothing to do with it to fail, for example, Flannel D. Okay, so our final lesson learned. So, right now you have deployed a Kubernetes cluster, or you've deployed a couple of clusters, you have been testing, it for a while in dev, you've deployed a whole bunch of microservices, you've taken things down, you've put them back up, you've learned a whole bunch of things. Great, now you're ready to deploy to production, everything's going to work great, awesome. Not so fast. Even if you do all that, it really, really helps to try to understand how the sausage was made. What are the various components, how they're built, how they're put together, and what issues or what design decisions they made. So I just put this slide up here. There could be a lot of discussions about this, but these are security concerns that wouldn't be obvious unless you really understood what the various components were, how they interact with each other, and how they operate. So for example, the communication between the API server and kubelet is broken. It's susceptible to man-in-the-middle attacks. This is something that was really true in the versions 1.1, 1.2, and later versions. It's gradually being fixed. Right now, most of the communication has been secured, but this really tells you that security was thought of as an add-on as opposed to being designed from the scratch. And there are things that have been fixed along the way, but we're still not there where we have 100% security. The other thing is you couldn't really completely disable the insecure port on the API server. This has now been fixed. It's not in the current version of Kubernetes, so it's not in 1.4, but it will be available in 1.5 and later versions. But one of the key things that's still outstanding for us from a security perspective is that certificate revocations is not supported. What this really means is that if you have a client certificate that's stolen, you really don't have any choice but to redeploy all your certificates, to rebuild the system, and go from there. Okay, so just to summarize, what our approach and what we hope you learn from this is, okay, try to deploy clusters, try to break them, try to take down nodes, try to see how it works. Secondly, basically, when you have a complex system with a lot of various components, a problem in one component that's not directly related to another component can take it down. So be aware of that. And finally, and this is where I really want to shout out toward the Kubernetes community and to the open source community. Try to understand how the system is built. And since Kubernetes, everything is transparent, everything is in GitHub, you can read all the issues, you can try to understand how it works, and you can really try to get a feel of what things have, or what design decisions were made and what things work. Okay, so with that, we're hiring in various different locations, London, New York, Princeton. Please contact Paul if you're interested, as we hope you will be. I'd like to give a shout out to Mike and Miko, who did much of the work that I presented over here. And with that, I'd like to open it up to questions. Thank you. Questions? Sir.
Paul, you mentioned that you're testing the microservices. They couldn't need any external footprints, couldn't change any external state. At some point, your application must change external state. How did you, unless it's just a feed, how do you deal with that?
Yeah, so I don't know if everyone got that. The question is, at some point, if you touch these external systems, you must have some kind of impact. I mean, we didn't really care particularly if, for example, we spewed in logs on some service that we were calling. That wasn't a consideration of ours. And similarly, it wasn't necessarily a consideration of ours if we call a service and we have some kind of degradation of service in that service, if that makes sense. What we wanted was that if we made a call to a service, so for example, a GET call, then every time we make that GET call, we should get the same response, and there should be no impact there. It's kind of like a slippery slope to start talking about idempotency and side effects and repeatability and stuff, because we didn't necessarily want that, because we didn't want the idea that you could, for example, delete a record in a database and keep deleting that record, and that would kind of be okay. That's definitely not what we wanted. So the way I always kind of think about it is kind of like almost embracing a functional paradigm, where we have very clearly defined inputs and outputs, and then it becomes exceptionally easy to test your code. It's trivial to test your code then. And the key thing to our mind was that business logic is the thing that varies all the time. It's not the interaction with the database or all these other kind of libraries and services. It's just like that computation that you do. So separate that, bring that out, make it trivial to run new versions of that, alternate versions of that, and give some really, really nice, clean way to test it amazingly well, and then we can release with confidence. That.
Other questions?
Well, please feel free to come and talk to us afterwards. Like I said, this is a production system that's been running for a year without Kubernetes, or probably 8 months without Kubernetes, and then the last 4 or 5 months on Kubernetes. So the initial version was significantly more naive than the version that we have now, so Kubernetes added a lot. I would say through that kind of process, we learned a lot more lessons than this. So people talked about Fluentd at the keynote speeches yesterday. I think we had a really interesting journey and over kind of log aggregation and log shipping. I think there's a lot of interesting conversations to have there. We use Prometheus at the moment, but we have different ideas or concepts of different types of logging within our system. So we use Prometheus for some data, and we use other kinds of data stores for other kinds of data as well. So, you know, if people want to come and pick our brains, please feel free.
Okay, thank you.